In this presentation, we focus on a core spatial planning decision in a container terminal, assigning vessels to berth positions when the timing dimension is simplified away. The point is to isolate the pure allocation question, so you can see how capacity limits, service rates, and priorities shape the best plan. You should think of this as the morning board assignment problem. A good allocation reduces overall service cost and prevents downstream bottlenecks that would otherwise appear later in cranes, trucks, and yard flow. The goal is to assign vessels to berths to minimize total weighted service cost. The static assumption means we treat the vessels as available for allocation at the same time, so we are optimizing spatial assignment rather than sequencing arrivals. Operationally, the difficulty comes from light heterogeneity. Berths have capacity limits and different service efficiency, and vessels differ in length, handling time, and priority. The solution must be both feasible and cost-effective. Every morning, the Port of Singapore faces a clear decision moment. At around 6 a.m., a fleet of vessels is waiting for berth allocation across discrete berth positions. The operations manager must decide who goes where, under size and operational constraints. A single allocation cascades through the terminal. It influences crane scheduling, truck movements, yard assignment, and ultimately the departure schedule. When allocation is poor, delay does not stay local. It propagates across the system. Even without arrival time sequencing, allocation is not trivial. Berth segments have hard length limits. Service rates differ across berths, and vessel priorities differ across customers and cargo types. Static allocation matters because it is the foundation. If you cannot make good spatial assignments under simplified assumptions, you will struggle even more when you add time windows, congestion, and uncertainty. We will solve the problem in tiers. Tier 1 is a complete integer programming baseline that defines the full model. Tier 2 is a weighted priority greedy heuristic for fast, deployable decisions. Tier 3 uses a genetic algorithm to improve global trade-offs beyond greedy choices. Tier 4 adds supervised learning for prediction and decision support. Tier 9 introduces a conceptual quantum approximation view using the quantum approximate optimization algorithm and a quadratic unconstrained binary optimization formulation. Tier 1 builds the correctness baseline. We model static berth allocation as an integer program, meaning we use binary assignment decisions and explicit constraints. The purpose of this tier is completeness and auditability. It forces you to define the sets, parameters, decision variables, the objective, and each feasibility rule so the plan can be validated and explained. This slide defines the core objects of the model. One set represents the vessels awaiting allocation. Another set represents the available berth positions. In plain operations language, these sets are the roster of vessels that need a berth assignment and the roster of berth slots you can assign them to. Parameters capture the terminal and vessel facts that do not change inside the decision. For vessels, key parameters include vessel length, priority weight, and handling time. For berths, key parameters include maximum berth capacity and a service factor that represents how fast that berth can handle work relative to others. These parameters define both feasibility and cost. The main decision variable is the assignment choice, whether a given vessel is assigned to a given berth. This is a yes or no decision. We also track timing-related quantities such as service start time and completion time, so we can measure the objective consistently and account for berth-specific service factors. The objective minimizes total weighted completion time. The weight reflects priority, so high-priority vessels contribute more to the total if they finish late. Operationally, the objective forces the solution to care about both efficiency and importance. It avoids a failure mode where the schedule looks efficient on average, but delays a high-priority vessel that the terminal cannot afford to delay. This slide summarizes the full feasibility rule set. First, each vessel must be assigned exactly once. Second, each berth has a capacity limit that must not be exceeded. Third, completion time must be computed consistently based on start time, handling time, and berth-specific service factor. Finally, variable domains must be respected. Assignment is binary, and time variables are non-negative. The assignment constraint ensures every vessel is assigned to exactly one berth. No vessel can be left unassigned, and no vessel can be assigned twice. Operationally, this prevents both omissions and duplication. It is the basic coverage guarantee that turns a set of candidates into a complete allocation plan. The capacity constraint ensures that the total vessel length assigned to a berth does not exceed that berth's maximum capacity. This is the hard physical feasibility rule. Without it, the model could fit vessels on paper that cannot physically berth in the available key segment. The completion time definition links decisions to cost. Completion time is computed as start time plus handling time, adjusted by the service factor of the chosen berth. Operationally, this captures that two berths can handle the same vessel at different speeds due to equipment availability, crane productivity, or local operational conditions. Domain constraints define what values variables can take. Assignment choices must be binary, meaning either assigned or not assigned. Timing variables must be non-negative. This prevents invalid solutions that cheat by using negative time to reduce cost. This slide provides a visual map of the key layout used for the berth allocation concept. It helps you connect the abstract berth indices to real terminal geometry. Use the visualization to sanity check assignments. If a berth segment is short, it cannot take a long vessel. If a segment is premium, it may be best used by a high priority or high workload vessel. This example uses 3 berths and 4 vessels. The berths have capacities 200 meters, 300 meters, and 250 meters. The vessels have lengths 150, 200, 180, and 120 meters, with associated priority weights and handling times. The takeaway is that feasibility and cost interact. A feasible assignment must respect capacity, but the best assignment also minimizes weighted completion. The illustrative total weighted completion time reported for the example is 94 units. Tier 2 provides a fast heuristic. Greedy methods are deployable in operations because they produce decisions quickly, but they are myopic because they commit early choices without exploring alternatives. Here, we compute a priority score for each vessel and then assign vessels iteratively to feasible berths. The design goal is to favor high-priority vessels that are short and quick to handle, while keeping assignments feasible under berth capacity limits. This slide shows the exact priority score used by the heuristic. Conceptually, the score increases when priority is high and decreases when the vessel is long or slow to handle. Operationally, this score encodes a rule of thumb. Prioritize vessels that deliver the most priority benefit per unit of berth capacity and per unit of handling effort. This visualization shows the flow of the weighted priority greedy method. You compute scores, sort vessels, and then place them into feasible berths based on remaining capacity. The key operational point is transparency. The heuristic is easy to explain to supervisors because every assignment can be traced to the score and to a feasibility check. This slide reports illustrative heuristic performance for 6 vessels and 4 berths. The total weighted service time is 167.89 units, and the average berth utilization is 89.2%. Interpretation matters. The heuristic tends to place high-weight vessels early into higher capacity berths. Feasibility is maintained by treating berth capacity like a packing constraint. This code part defines the vessel and berth data structures and computes the priority score for each vessel. As you read, focus on how the score uses priority weight, vessel length, and handling time. This is where the operational policy is encoded. This section sorts vessels by the priority score and begins the iterative assignment process. The key detail is feasibility. A vessel can only be assigned to a berth if the remaining capacity can accommodate its length. This part performs the actual placement step and updates berth capacity after each assignment. This update is what makes the heuristic consistent. Without updating remaining capacity, the algorithm would produce assignments that look good but do not fit. This final section reports results and metrics, such as total weighted cost and utilization. Those metrics are essential for comparing the heuristic to the baseline model and for deciding whether the heuristic is good enough for the current terminal conditions. Tier 3 moves beyond greedy choices using a genetic algorithm. The idea is to explore a population of allocation solutions instead of committing to a single incremental path. Key design choices include the chromosome encoding, a fitness function that reflects objective and penalties, and evolutionary operators such as selection, crossover, mutation, and elitism. The fitness definition acts as the scoreboard for candidate allocations. It should represent weighted service time, include penalties for any constraint violation, and encourage high berth utilization. Operationally, fitness design prevents cheating. If penalties are too weak, the algorithm may prefer infeasible solutions. If penalties are too strong, the algorithm may ignore efficiency improvements. This slide visualizes the genetic algorithm loop. Initialize a population, evaluate fitness, select better solutions, apply crossover and mutation, and repeat. You can think of this as systematic trial and improvement. Instead of relying on one greedy ordering, the algorithm searches across many allocation patterns. This slide reports illustrative genetic algorithm results for 8 vessels and 4 berths. Best fitness is 487.34 at generation 247. The total weighted service time is 142.67 units. Average utilization is 91.3%, and there are 0 constraint violations. The message is that population search can improve global trade-offs beyond greedy decisions. This code part defines the chromosome representation, meaning how a candidate allocation is encoded. Look for how a gene maps a vessel to a birth index. Encoding is the foundation because everything else depends on being able to generate and decode allocations consistently. This section defines how fitness is computed for a chromosome. It calculates the cost terms and applies penalties for violations. The operational goal is to ensure that better fitness corresponds to an allocation that a terminal could actually execute. This part implements selection, such as tournament selection, and defines how parents are chosen. Selection controls pressure toward better solutions. Too much pressure can reduce diversity, while too little pressure can slow improvement. This section implements crossover and mutation. Crossover mixes assignments from 2 parents, and mutation makes small random changes. Operationally, these operators must preserve interpretability. They should generate new allocations that are plausible variations, not chaotic noise. This part includes elitism and population update logic, preserving top-performing solutions while exploring new ones. Elitism improves stability. It reduces the risk that the algorithm forgets the best allocation found so far due to random variation. This final part reports convergence, best fitness over time, and the final allocation result. These outputs matter because they provide evidence of improvement and show when additional computation stops yielding meaningful gains. Tier 4 shifts from solving each allocation instance to predicting good allocations. We train supervised machine learning models on historical allocation decisions and outcomes. The goal is decision support. The model can suggest birth assignments and expected performance, helping operators act faster when conditions are stable and data is rich. This slide shows the ensemble architecture. Instead of relying on one model, we combine multiple model families to improve robustness. Operationally, ensembles can reduce the risk of overfitting and provide more stable predictions when the data distribution shifts. This slide reports illustrative predictive performance. Training accuracy is 88.4% for assignment classification. Performance prediction error measured as root mean squared error is 2.1 time units. Cross-validation confidence is described as 0.83 plus or minus 0.07. The key idea is not just prediction, but calibrated confidence, so operators know when to trust the recommendation. This code part sets up the dataset and feature engineering pipeline. Focus on what features represent operationally, such as vessel priority ratios, compatibility indicators, and birth capacity relationships. This section defines model training for one or more algorithms, such as tree-based models. The important operational point is repeatability. Training must be consistent, and data splits must reflect the way decisions will be made in practice. This part continues training and includes evaluation logic. Evaluation should reflect both assignment correctness and the ability to predict performance outcomes that matter to operations. This section adds additional models or ensemble combination logic. Operationally, combining models should improve stability, not just maximize one metric on a narrow dataset. This part includes prediction and possibly confidence or probability output. Confidence output is valuable because it tells supervisors when the model is uncertain and when a human review is warranted. This final code part reports metrics and summarizes the model outputs. The key operational takeaway is that prediction can be used as decision support, but the system should still be auditable and monitored. Tier 9 reframes berth allocation as a quadratic, unconstrained binary optimization problem suitable for quantum approaches. The core idea is to encode both objective and constraints into an energy landscape. This is presented as a conceptual extension. Today, practical use is limited by the number and quality of available qubits, but the formulation shows how allocation can be mapped into quantum-compatible structures. This slide shows the energy function used in the quadratic unconstrained binary optimization formulation. It combines assignment costs with penalty terms that enforce one berth per vessel and capacity feasibility. In plain terms, the penalties make it expensive to violate constraints. A low-energy solution corresponds to a feasible allocation with low service cost. This slide shows the quantum approximate optimization algorithm state construction as alternating layers that encode the problem and mix between candidate solutions. Operationally, you can think of this as a structured search process that explores many allocations in parallel in a quantum representation, then biases toward the best ones. This slide visualizes the quantum circuit architecture used for the quantum approximate optimization algorithm framing. The main takeaway is conceptual. As hardware improves, such circuits could evaluate structured allocation problems faster than classical exhaustive search for specific instances. Use these questions to test whether you can implement the methods from this deck. Practice building the full integer program for a small instance and verifying feasibility. Then implement the greedy heuristic and compare key performance indicators. Implement the genetic algorithm and analyze convergence, and implement machine learning features and evaluation. Finally, explain how quadratic, unconstrained binary optimization penalties enforce assignment and capacity rules. Static berth allocation is a core spatial optimization problem in terminal operations. Tier 1 provides a complete baseline model, Tier 2 provides a fast and deployable heuristic, and Tier 3 improves global trade-offs through population search. Tier 4 adds prediction with uncertainty estimates for decision support. Tier 9 offers a conceptual roadmap for future quantum acceleration, showing how allocation objectives and constraints can be embedded into an energy-based formulation.